Hello everyone, thank you for attending my presentation. My name is Andreas Michael and I'm with Cipriana Petroleum Technology. The title of my talk is PIMPS3D2P, a practical, efficient, three-dimensional two-phase reservoir simulator written in MATLAB. Pretty self-explanatory title. PIMPS stands for Program for Integrated Modeling of Petroleum Systems. And the idea of me writing this code was born during my graduate school years. My research was on fracture initiation. However, I had a lot of free time, and I did put a bet with one of my friends that a three-dimensional two-phase reservoir simulator can be written fully in one MATLAB file and take less than 500 lines of code. Now, I obviously won that bet. I think it took me something like 390 lines of code, but what I really like about this exercise that I forced myself doing was that unlike many of the students who go to school and they learn how to use some commercial reservoir simulators in a black oil manner, they basically put some inputs, get some outputs, they see if they make sense more or less, and they move on. At least I came up with a functional code which I can adapt to different parametric studies. Of course, it's going to be simple, fairly basic, but still I understand every step of the process. And since I further developed that code that I wrote, I made some developments regarding computational speed, stability, and yeah, it's a fairly simple tool, but something that I believe that every good petroleum engineer should have in his quiver. Now, an overview of my code is that three-dimensional, two-phase water and oil. So it's good for simulations above the bubble point. A finite differences model, which implies that inputs and outputs are indicated at nodes, at each node, not at each grid block, at the nodes around each grid block. And it's under mixed implicit explicit scheme. When I did the first version of that code, it was IMPES, implicit pressure, explicit saturation. However, by switching to Crank-Nicolson, I did manage to achieve better, being able to have stable simulations under a higher time step with not much more sacrifice in the computational speed, a very tiny bit. And of course, it's written in one MATLAB script file, and actually writing it in one script file was more or less the rules of the bet. However, you can make a more tidy code if you divide it to many function files, and then you have a master function file calling each of them, and the master function file is what is used for the graphic user interface, which is also possible to make through MATLAB. Now some words on the basic reservoir model, simulation inputs and outputs. The values of both inputs and outputs are updated at every simulation time step. The gap between each time step is between time steps is delta t, and the values of the inputs and outputs, like I said before, are given on each node. Here we have the inputs we have phi, which is porosity. We have K, which is absolute permeability. We have Kr, which is relative permeability for two-phase flow. We have total compressibility. We have, with Ct, we have ρ, which is the fluid density. We have the Greek letter mu, or as the Greeks call it mi, which is the fluid viscosity. B for the formation volume factor. P underscore C, which is the capillary pressure, the difference in pressure between the non-wetting phase and the wetting phase. Z, which is the elevation from a reference datum, normally the base of the model. And then Q, which is the well flow rate, used as a boundary condition. And PWF, which is the bottom hole flowing rate, bottom hole flowing pressure, which is also can be used as a boundary condition. Now, many of those property values, when we have a two-phase flow, they vary for each fluid phase. In this case, we have water and oil, and we use the subscripts W and O to distinguish between the values of each parameter for the water phase and the oil phase. So those parameters, which is permeability, relative permeability, viscosity, formation volume pressure, and well flow rate, we have two values for each simulation time step, one for each phase. And then we have the outputs, which for this simulation reservoir simulator, they are very simple. They are the pressure at each node and the saturations at each node, the water saturation and the oil saturation. For those outputs, we need to specify their values at the beginning of the simulation before the first time step. So it's good to create, I guess that's the only way I know how to do it, is to create vectors or matrices which will have the values of each of those parameters at step 0 before simulation step 1. That would be the initial reservoir pressure, the initial water saturation, and the initial oil saturation for each node. For the simulation execution, we have some intermediate parameters, like the transmissibility matrix, which is measures the ability to transmit fluid from one node to another. For a three-dimensional reservoir simulator like my own, we have a heptadiagonal transmissibility matrix, which means that the matrix is a peak square matrix, which has a number of rows and number of columns equal to the total number of nodes of the reservoir simulator, and 7 diagonals are containing or are able to contain a non-zero value, non-zero values. The reason being is that in its most complex configuration, the A node can be surrounded by 6 other nodes above, below, right, left, back, and front, from which it can interact, either receive fluid or give fluid, and also that node can have a wellbore going through from where it can be accumulating flow or rejecting flow. So there are 7 ways that a node at max can be receiving or, I guess, emitting fluid. The accumulation rate matrix, D, is related to the time step and gets bigger with a smaller time step. The productivity index matrix is related to boundary conditions when it comes to wells. The source vector Q is also related to wells with a constant flow rate. And the gravity and capillary pressure vector G is related to gravity and capillary pressure effects, which are normally almost negligible. At the first step of our simulation execution, we evaluate the pressure at each node for time step n+1 using the corresponding values at the previous time step n. And this is achieved by performing this equation with the matrices and vectors in bold. Then we use the values of the pressure at time step n+1 to calculate the water saturation for that particular time step, also n+1. And we are using the values of the water saturation in the previous time step. We can do the same for oil saturation, is no big deal. And the next time step is a very simple mass balance equation to calculate the oil saturation values at time step n+1 using the previously calculated water saturation values at the same time step, or vice versa. Now this is the flow chart of how the code works. And as you see, it allows a variation of every input other than the initial conditions and the initial conditions of the inputs and outputs. Because everything else is within the time loop. So if any of the input parameters varies within the time loop, we allow for it to vary as such, and it's going to affect the outputs accordingly. At the end of the simulation, we use the results to create visuals and plots. Now, some tips for using MATLAB. The first two equations that I used in the code, they are in the form AX equals to B. And this can easily be solved in MATLAB using the powerful / function. So you are trying to solve the equation AX equals to B, where A is a matrix and X and B are vectors. X is the unknown vector. You just type X equals A / B and you will get the answer. Once the simulation is completed, the values from the final output vectors, pressure, water saturation, and oil saturation at each node, contain the output data, and they are used to create visualization, which is what I showed, the pictures I showed, the 3D block model. I use MATLAB's surf function to create 6 two-dimensional surfaces on the edges of the simulated 3D block. And then I use the interp function at each grid block face to color it according to the average value of the 4 surrounding nodes. MATLAB's default functions, they have the tendency to color the grid block face according to the bottom left node, and that will create an offset in the way the results are visualized. So if you use interp function, it makes it look correct. Now, boundary conditions is a big issue when it comes to reservoir simulation. And there are two main kinds. The first one is constant flow rate, or Newman boundary condition. And it's approximated by specifically pointing out flow rates at given nodes where that boundary exists. And then we have the constant pressure boundary, Dirichlet, which is slightly more complex and is approximated using imaginary grid blocks adjacent to the boundary. I use an example here to explain the basics of that. If we try to simulate a block of a reservoir where it has a well in the middle, which is producing at a given rate, and is surrounded by 3 no-flow boundaries, which are Newman, and 1 constant pressure boundary, which is Dirichlet, we can achieve that modeling-wise by inserting an identical size reservoir by that Dirichlet boundary, however, the well in its middle, instead of producing at a given flow rate, to be injecting at the same flow rate. This will double the simulation time at least. It's an inefficient way of doing it. However, with modern simulation methods, by using imaginary blocks, we can achieve that in a more efficient way by varying some of the parameters. Sorry, not by using imaginary grid blocks, by varying the value of some of those matrices and vectors in the equation. Finally, we verified and validated our model. I verified and validated the model by comparing the results against the known solution and seeing how well the reservoir simulator can replicate this pre-established solution. The first problem that I use is known as the Ramey's problem because it was taken from Hank Ramey's book from 1973. It involves a rectangular reservoir of length and width of 2,000 feet and height of 50 feet, with a vertical well in the middle producing at 500 Stockton barrels a day. Dr. Ramey, a professor at Stanford at the time, he analytically calculated the values of the bottom hole pressure for the first 115 days and published that. So I was able to run my simulator and compare my results to the established solution of Dr. Ramey and see how well it matches. The second problem that I did for validation purposes, it was a numerical problem using Deleu's work from 2014, where for his master's thesis he wrote a reservoir simulator not much different than mine and ran a simulation for horizontal wells, again using a rectangular reservoir of different length this time and width of about 3,000 feet, with a 1,000 foot long horizontal lateral going through, as we see here. Now, Dele published the average pressure of the entire reservoir, the maximum pressure, and the minimum pressure for dimensionless time. And I was able to run the same simulation on my code and compare my results to see how well it matches the solution. And as you see from the plots, it did a very good job. In conclusion, a robust multi-purpose 3D two-phase reservoir simulator was written efficiently in one MATLAB script file with very few lines of code. The simulator was verified analytically and validated numerically using Ramey's and Deleu's solutions. This simulator can be easily adapted to model any parametric study, giving it immediate numerical results similar to those that expensive commercial simulators produce at a much, basically free. And it can serve as a useful primer for anyone exposed to reservoir modeling for the first time. And that's a tool that any self-respected reservoir engineer should have in his arsenal. It's not about being able to use a commercial simulator. It's more about being able to understand how it works in every detail. And with that, thank you very much.